So, um, so what we're doing in this 9.1 is emphasis about two proportions. So we're doing a very similar thing that we did last week with instead of doing one proportion, being whatever greater than 20% or whatever it may be. Now we're looking at two proportions to see if they're equal or different. Okay, are the proportion of males that pass the class and the proportion of females that pass the class the same, or are they different? Okay, so we're looking at two different portions to see if how they relate to one another. We have similar assumptions as before. We have both have to be SRS, simple random sample, and are independent. So we have two groups. When we say independent, they can't have any effect on one another. So for instance, if I talk about the proportions of males that pass the class and the proportion of females that pass the class, those are two independent groups. Assuming that the males or females are not cheating off one another or something like that, they should be two independent groups. And then we have to have at least 5 successes and 5 failures in each of the groups. So we have to have at least 5 males pass, at least 5 males fail, same for the females. Okay. Now, what really changes from the last chapter to this one is that we have a giant test stat. Okay. So this test stat, the reason why it's so enormous is because we're looking at two proportions rather than one. Now, I'm going to talk quickly about this and how how this differs, but the main thing is we're going to be doing all this on StatCrunch, and it'll eventually figure it out for us. So let's see what we have. So we have two sample proportions, P1 and P2, P hat 1 and P hat 2. Those would be our two sample portions. So that example I talked about, the percentage of males and females that pass, those would be our two samples. Okay, so maybe P1 is the proportion of males that pass, P hat 2 would be the proportion of females that pass. Now, we also have this P1 and P2. Those are hypothesized differences. So in all our examples, we're going to assume that the P1 equals P2. So on all our examples, this is going to be 0. Okay, so on this example would be that the portion of males and the portion of females that pass the class would be no different, which is what I would expect. So we're always going to have that go to 0. And the only thing we have is this P bar Q bar, and P bar is the pass rate regardless of gender. Okay, so we take the total number of students and the total number that pass and disregard everything. So everything else. So we just take the total number that pass over the total number in the class. Okay, and then N1 is our sample size of the first group, say the males, and 2 would be the sample size of the second group. Okay. All right, so this looks horrible, but it's actually going to turn out to be pretty much the same as what we did before. We do have a confidence interval. I'll come back to this. I'm going to speak quickly about it now. We have the difference between the two sample portions, and then we have our plus or minus. This is our value of 2, and this is our standard error. So we're going to basically, find the difference between our two sample proportions, and then add and subtract our two standard errors. So the same thing as we've done before. It's just, again, much more complicated because we have two proportions rather than one. Okay. All right. So let's look at this problem, and I'll go through this one slowly. And of course, if you have any questions, please stop me. And this is, I think, it's actually one of my favorite problems in the course. I like this one because it just defines what we're trying to do in this section perfectly. All right, so in this problem, it says, in a randomized controlled trial in Kenya, insecticide-treated bed nets were tested as a way to reduce malaria. So it says among 343 infants using bed nets, 15 developed malaria. Among 294 infants not using bed nets, 27 developed malaria. We want to use the 0.01 stimulus level to test the claim that the incidence of malaria is lower for infants using bed nets. Okay, so let's talk a little bit about malaria, make sure we understand what they're asking, what they're talking about. So we don't have malaria in the United States, but a lot of third world countries and stuff, they still have malaria, and it's a problem. And the way it is spread is through mosquitoes. So you can get bit by a mosquito, and they can transfer this malaria, and you can get very, very sick and in some cases die from this. I actually spent some time in the Amazon River Basin and saw a couple people that were living there that had malaria, and they were in pretty rough shape. The group I was with, helped one family transport a lady downriver that had malaria, and she was so sick that she couldn't even sit up in the boat. I don't even know if she made it or not. It is close, I would say. She was pretty sick. So what they sometimes use is bed nets, and a bed net is exactly the way it sounds. It's just a net that goes over your bed. And the idea is that, if you have this net that goes over your bed, the mosquitoes can't get in at night. And if the mosquitoes can't get in, they can't bite you. And if you get less bites, there's less less malaria. Okay. So we have these two groups, and what it says to do, it says, use a 0.01 stimulus level test to claim that incidence of malaria is lower for infants using bed nets. So we have these two groups, and what we're saying is the bed net group should have less malaria cases than the no bed net group. Okay, so we're using a less than. All right, so just like last week, we have our step one is finding HO and H1. So our HO is that proportion of the bed net group and no bed net group are the same, meaning the bed nets don't work. So it doesn't matter if you have a bed net or not, you still have the same rate of malaria. And our H1 is that the bed net group has a lower rate of malaria than no bed nets, meaning the bed nets work. Okay, so our two cases are, we assume that the bed nets do not work unless we can prove otherwise and show that they do work. Now, this gets messy. Notice that I have all this worked out by hand. Do not work it out by hand. It's a mess. Okay, because we have two proportions, and it just gets to be a mess. But when we get down to this test stat, this value is just the difference between how far these two groups are apart. And the bed net and no bed net group turned out to be negative 2.44 standard errors apart. So our cutoff is around 2. So they're far enough apart to say, oh, there's a difference between the no bed net and bed net. In other words, we're thinking this bed net is probably working here. Okay, so let's see what we do from there. All right. So the first three steps are the exact same as what we did last week. We have to find our HO, H1. We find our alpha. We find our test stat in step 3, and then we find our p-value. Since this is a left tail test, we got to find just the left side for the p-value. Okay, so the p-value is left side, so less than the test stat of negative 2.44, and we get the p-value of 0.0073. And I'll show you how that works in StatCrunch here in just a minute. Okay. All right, and then we go right back to our step 5. If the p-value is low, HO must go. So if our p-value is 0.0073 and that's less than alpha 0.01, then we reject HO. Okay. So as soon as we reject HO, it no longer can be that, and we assume that it's got to be less than. Okay, so in other words, we just show that the bed nets work. All right. And then 6 is our final conclusion. That's where we have to go to our table, depending on what case we have. And in this case, there's sufficient evidence to support the claim that the incidence of malaria is lower for infants who use bed nets. Okay, so we just showed that the bed nets work. So this is kind of what this is for. We're trying to show if a drug works. We're trying to show if these bed nets help. We're trying to see if there's a difference between these two proportions, and in this case, there is. Okay. right, let me hesitate there or stop there. Do you have any questions on that part? Okay, so let me do that in StatCrunch. I got to write down these numbers, so I have to have the you know, in the BedNet group we had 343 that were sampled, and 15 of them got malaria, and another other group was 294 and 27. Okay, so let's see how this changes for StatCrunch. So we're going to go under stat, and we have proportions. We're talking about two different proportions. So we go under proportion stats. And now here, the only difference from last week is instead of going under one sample, we're going under two samples because we have two proportions rather than one. Okay, so we got two sample and then with summary. We have to enter in those two groups. So we had 15 successes out of 343. And we had 27 successes out of 294. Okay, so those are two groups. Just like I said before, we always assume that P1 equals P2. Now, when we go to StatCrunch, they look at the difference between the two. So let me go back to our thing. So the book uses P1 equals P2. So we're assuming that they're equal. So when we go to StatCrunch, they look at the difference. So the difference between two things that are equal is always going to be 0. All our cases, this is always going to be 0. We're never going to change that. Always going to be 0. Okay, so don't need to change that. And then we have to find the alternative, which is less than. Okay, so it's a left tail test. Once we hit compute, we have our step 1 here, the HOHA. Step 2 is our alpha. Here's step 3 and 4 here. Okay. And then we just have to compare the p-value to our alpha. If the p-value is low, HO must go. And then our final step 6, is our final conclusion. Okay, so again, very, very similar to last week, just a more complicated test stat. And, you know, as long as we give StatCrunch the correct information, it'll actually calculate our test stat there at step 3. Okay. All right. Now, all right. Any questions on that? Okay. Now we're going to build a confidence interval for these bed nets as well. Now this is a little confusing at first, and we're going to do several of these as today to hopefully clear this up. But let me explain what we're trying to do. So I'm going to go back up to this problem, and I want to point out a couple things. We have an alpha of 0.01, and we have a left tail test. So what that means is we're putting the full alpha in that lower tail because it's a left tail test. So this tail should be the value of 0.01. Now, when we switch to confidence intervals, a confidence interval is not directional. It doesn't just have a left side or just a right side. We go in both directions every time. Right? So when we switch to confidence intervals, whatever we have in one tail, and like this case 0.01, we also have to put in the other tail. So we have 0.01 in both tails. So if we have 0.01 in the left and 0.01 in the right, what's left over in the middle is 0.98 or 98% confidence interval. So it's not a 99, it's a 98. Okay. So I explained that in this little blurb here, you know, saying the same thing is, you know, if we have a one-tail test, we have to put the alpha in both tails, reducing the confidence level down more than we would expect. Now, I've worked this out by hand. This is super messy. So here's our 2 point estimates. The group with the bed nets had about 4% malaria rate. The group with no bed nets basically had a 9% malaria rate. and then we add and subtract our 2 standard errors from that. Okay, so this is a giant mess, and what comes out is this confidence interval from negative 0.09 to negative 0.00118. All right, now let's figure out what that means. What that is the difference that the bed nets are making. It's not the rate of malaria, it's the difference the bed net is making. So what it's saying, it's reducing the malaria rate somewhere in between 0.001 and 0.095 decimal places, or I guess it's actually 9.5% to 0.1% lower than it would be without a bed net. Okay, so the bed nets are helping by this much. Okay, so let me explain that again. So when we did this, the rate of malaria out of our sample for not using a bed net was around 9%. Okay, so if you don't do anything, don't use a bed net, the rate of malaria is around 9%. When we look at the confidence interval, what that says is it's lowering that 9% by just a little bit, by 0.1%, all the way to 9.5%. So it's lowering it from just a little bit to almost, well, essentially all of it. Okay. So there's going to be a follow-up question on each one of these that's going to ask, does the confidence interval agree with a hypothesis test? Okay. The answer to that is always yes. So again, there's going to be a follow-up question, does the confidence interval and the hypothesis test agree? And the answer is always yes to that. And then they're going to say, basically, why? And the reason, the answer they're looking for is you're looking at this confidence interval to see if 0 is in that range or not. So notice that these are both negative. Okay. Well, we assumed that these two are equal, so the difference between them would be 0. Okay, so HO is the difference is 0, and what the confidence interval is saying, no, the difference is not 0. There's a whoops. They're both negative, so 0 is not in that range. So since we rejected HO, 0 is not going to be in there. If we failed to reject HO, 0 would be in there. Okay, I'm going to take a second to let you guys digest that. Does that make sense?
The only thing I'm confused about is that the original one, P2, being like 9.18% up above, which I get is like, hey, if you don't use the bed net, 9.18% right there,
right.
P2.
Right.
And then we go down, and you're saying that the confidence interval can reduce it by these two numbers being 9.5 or, pretty much nothing. It's saying that we can reduce it below the percent that it already is, obviously.
Right. Well, right. I mean, basically it's saying we can reduce it by a little bit or all the way to pretty much completely eliminating it. It is a little bit strange that, it's reducing it more than what our sample is.
Right.
So yeah, I see that's a little bit funky. But you realize that this P2 is just an estimate. So,
Okay. Because at first I thought
so
you were saying that confidence interval was reducing 9.18% by 9.5%, obviously, which would only be about like at 8. It would then put it at 8%. But I realize you're saying the total.
Yeah. So this is an estimate. So, maybe the true percentage is, 10%.
Right. Okay.
And so, what it's saying is it's reducing it by quite a bit on that end. On the other end, it's just reducing it just a tiny bit.
Yeah, I guess it makes sense why it's an interval instead of,
Yeah, it's that's a little strange, but good that you caught that. Okay. All right, so let's see how this works out in StatCrunch. I'm gonna enter those same. I'm gonna do the exact same thing as I did before. I'm gonna go stat, portion stats, to sample with summary. So the exact same place I just went. I have to enter those values in again. So we had 15 successes out of the first group out of 343. And we had 27 successes out of 294. Okay. Now, we did the hypothesis test. Now we're going to go down the confidence interval and do that. And we put in 98%, for the reasons I mentioned before. Okay. And we hit compute. We're going to have that upper and lower limit that we found by hand. I would highly recommend this. Again, the follow-up question will be, does this confidence interval correspond with the hypothesis test? The answer to that is always going to be yes. And then they'll say why. And you'll either say 0 is in this range or 0 is not in this range, depending on whether you reject or fail to reject HO. Okay, so if you reject HO, 0 is not going to be in there like it is here. If you fail to reject, then 0 would be a possibility, meaning that one of the possibilities is there's no difference. Okay, does that make sense? Because I know this is not automatic by any means.
For the confidence interval, can you just run through how you did it on StatCrunch one more time?
Sure. So I go to let's start from scratch. Why not? So we go under stat, proportion stats, to sample with summary. So that we're going to the same place for the confidence interval and the hypothesis test. Okay, so stat, proportion stats, to sample with summary. Then we have to enter in the number of successes and trials for each group, which is 15 and 343 and 27 and 294. And then we go, instead of leaving it on hypothesis test, we go down a confidence interval and put in this case, 98%. Okay, is that helpful?
Yeah, just where again are we getting the 98%?
Okay, so that so they told us that we have an alpha of 0.01. Okay, but we only have a one-tailed test. So we have alpha 0.01 in the left tail. When we switch to confidence intervals, there's no such thing as just a one-sided confidence interval. So we have a two-sided, so we're kind of forcing a one-tail test to be a two-tail. So whatever's in one tail has to be in the other. So if we have 0.01 in the lower tail, we have to have 0.01 in the upper tail. So if we have 0.01 in each tail, what's left over in the middle is 98%, 0.98.
Got it. That makes sense.
Okay. And we're going to do a few of those. It's not automatic first time through. Okay. All right. Any other questions on this one? Okay. All right. Next thing is emphasis about two means. Okay. Same idea, but now we have two means. The mean SAT score for males and the mean SAT score for females. Are those the same? Okay. So the same idea. Are we looking at two different samples? Are those the same or are they different? Okay. But instead of proportions, we're just looking at means. Okay. So our assumptions, we have population standard deviations are unknown and no assumptions made about the quality of them. There's actually a couple different cases of this. This is the simplest and most common, which we're assuming that we don't know anything about the population standard deviations and we don't care if they're equal or not. Okay. We have independent samples, simple random samples, and we have to have large samples above 30 or normally distributed. One of those will work. Okay. So what we've changed from the last section of this one is we've changed our test stat. We're measuring different things, so our test stat changes. Okay. So here's our two groups. The mean SAT scores for the males, mean SAT scores for the females. Are those the same or not? And then our hypothesized difference. We, again, always assume this to be 0. We assume that both the males and females would have the same SAT scores. Okay. We have the standard deviation of the first group squared and standard deviation of the second group. and then the sample size of each one of the groups. Now, what we're going to use for degrees of freedom, we're going to look at whatever group is smaller and subtract 1 from it. That's not how StatCrunch is going to do it. There's a whole calculation for the degrees of freedom for this. And the calculation for the degrees of freedom is more complicated than the actual problem itself. So we're just going to use the more conservative, easier way if we do it by hand. And when we use StatCrunch, we'll see that degrees of freedoms are different, and they'll have slightly different answers. In my stat lab, they recognize that some people are using it, by hand, some people are using, a program, and they'll accept both answers. So we're going to see slightly different numbers. Either way is fine. Okay. Again, using this degrees of freedom here is just more conservative, but also easier. And then we have a confidence interval, same idea as before. We have the difference in the two means, plus or minus our, so here's the difference of the two means, plus or minus our 2 standard errors. Okay. And again, we'll do the same thing with degrees of freedom. All right, so let's see how this works out. So data set 5 in Appendix B lists the full IQ scores for a random sample of subjects with low lead levels in their blood and another random sample of subjects with high lead levels in their blood. The statistics are summarized below. Use a 0.05 significance level test to claim that the mean IQ score of people with low lead levels is higher than the mean IQ score of people with high lead levels. Okay, so that last sentence is a little bit of tongue twister, so we had to read that slow and figure out what we have. So we have these two groups that have different levels of lead in their blood. And what this claim is, it says use a 0.05 significance level test to claim that the mean IQ score of people with low lead levels, okay, so the low lead level group, is higher than the mean IQ score of people with high lead levels. So we're expecting that the low lead level people are going to have higher IQs than the high lead level people. In other words, lead makes us not so smart. Okay, so let's see how that works out. We have our HO and H1. We always assume that they're equal, meaning there's no difference between having lead in your blood or not. And our claim is that the group with low lead levels have higher IQ scores. Okay? In other words, the high lead level people have damage to their IQ. Okay. All right, so the test stat, we plug in all our values. Again, we always assume that our difference is 0. Okay, we assume that they're equal, so the difference would be 0. We plug in all those values, and we find our test stat at 2.282. So that's pretty good ways out there. That's outside 2. Okay, so I'm thinking we're probably going to reject here. And here we find the p-value, and here we do it on the right side because it's a right tail test. Okay. So our p-value in this case is 0.168. And we go right back to our standard thing. If the p-value is low, HO must go. So the p-value is 0.168. That's less than 0.05. So we reject HO. So if we reject HO,
I don't know if it was just for me, but your screen went away.
Oh, okay. What did you miss?
No, like it's not on. Like you're not showing up. I don't know if it's right. There you go. No, you just came back.
Okay. So. Okay.
I don't know if that was me.
Okay, you messing me up, or am I messing myself up?
Yeah, now your screen just came back. I don't know if that was me or you. I'm sorry.
Okay. We're gonna blame it on you. I mean, for obvious reasons. All right.
Yeah, if you could just do the test stat one more time.
Okay, sure. All right, try not to mess me up, okay? All right. So we have this test stat. We assume that the mu1 and mu2 are the same, so that we assume that whether you have high or low level of lead in your blood, it makes no difference. So your IQ score would be the same. Therefore, the difference would be 0. We're always going to assume that that's going to be 0, okay, in all our examples. So we just have to measure the difference between our two samples. And we plug in all the given information, and we'll have StatCrunch do this for us. And we find that the difference is the 2.282. This is a right tail test. Okay, it's greater than. So when we go to find the p-value, we want to find, above our test stat. Okay, so that's where we get the 0.168. Again, StatCrunch will do this for us. Okay. And then we're right back to our standard procedure. If the p-value is low, we reject HO. Again, the p-value is 0.168, which is less than alpha. So we want to reject. Our final conclusion, we want to go back to our table to figure out which case we have, whether we reject or fail to reject HO and what our claim is. So in this case, we rejected HO and our claim was strictly greater than. So in this case, it would be there's a sufficient evidence to support the claim that the mean IQ score of people with low lead levels is higher than the mean IQ score of people with high lead levels. So what we just proved is that lead is not good for us. Okay, so we already know that now, but back in the day, people didn't know that. So we're using lead paint and we're using lead in our gasoline and so forth. So this shows that that was not a good idea. So that's why we changed things. All right, now let me have to write down all these numbers here. So we're going to have to, I'm going to show you how to do this on StatCrunch. I'm writing all these numbers down so I can bring in the StatCrunch. So we have our N of 78, our mean of 92 and change, and a standard deviation of 15 and some change. Okay. And then the high lead levels, we have N of 21, mean of 86 and some change, and standard deviation 8.9, 88352. Okay. So let's see where we go. Notice our test stat is a T. So we're going to go under stat, T stats. And again, this is where it changes. We're not going to use one sample in this case because we have two samples. We're comparing the two groups of the low lead and the high lead level people. So we go to sample with summary. Okay. So now I got to enter all this in. So the sample mean is 92. Bear with me here. 92.88462. Our standard deviation was 15. Sample size is 78 and 86. Okay, so we enter in all our data that's given, and then we have to look at our hypothesis. We always assume 0. Okay, so we assume that HO, there's no difference between the two. And our alternative was a right tail, so we want to put greater than there. We hit compute. We gave it step 1 here. Step 2 is our alpha, which was 0.05. Step 3 is our test stat. Step 4 is our p-value. Again, those are going to be slightly different than ours because we use different degrees of freedom. And then step 5 is comparing p-value to alpha. The p-value is low, we reject HO. And then finally, our final conclusion would be using our table. And we concluded that there is a difference whether you have high lead levels or low lead levels in your blood. It does change your IQ score. Okay. All right, now. So what we just concluded is that we rejected HO. So therefore, we think the IQ scores of the low lead level people is higher than the high lead level people. Okay, so we just concluded that. Now, when we do a confidence interval, HO means there's no difference, meaning that 0 is still a possibility. but what we concluded is 0 is not a possibility. So when we do our confidence interval, I'm expecting to have both our limits to be positive. Okay, let's see what that looks like. So we want to build a confidence interval. Now I have a 90%. Now let's figure out where that 90% comes from. Okay, so this is, we have an alpha of 0.05 and a right tail test. So when we're doing the hypothesis test, it's a right tail test, so we put the full alpha in that right tail. So we have the 0.05 in that right tail, which works fine for the hypothesis test, but when we do a confidence interval, we also have to put the same thing in the lower tail. So if we put 0.05 there, what's left in the middle is a 90%. Okay? So we would have a 90% confidence interval in this case. Okay? If it was a two-tailed test, we would split up the alpha right off the bat. So if it was a two-tailed test rather than one tail, we'd split up the 0.05 in either tail. Or I'm sorry, we'd split the alpha of 0.05 into both tails, so 0.025 in both, and it would be a 95% in that case. So we have to be careful every time. If it's a one tail, we have to reduce it even more than we realize. If it's a two tail, we split it and it would be a 95%. So we have to check that every time. And I think we have an example of that at the end. So to build a 90% confidence interval, I've done this by hand. I do not recommend this. So here's the difference between the two IQ scores. And then we add and subtract our two standard errors. And we get this range from 1.4 to 10.4. So what that's saying is the group that has low lead levels in their blood have IQ scores that are higher by 1.4 to 10.4 IQ points. Okay, so this is the difference in the two groups. Okay, so the low lead level people have higher IQs by 1.4 to 10.4 points higher than the high lead level. Okay, which corresponds with what we concluded, that we concluded that H1 is true. So the low lead level people have a higher IQ score than a high level people. Okay. I'm going to cheat here, so I'm going to have to enter all those numbers again and just go back to edit. So we go to the same place. We go T-stats to sample with summary. We enter in all data like we just did, and then we just go down to confidence interval, and we put in 90% as we discussed before. Then we have our upper and lower limits. The follow-up question will say, does a confidence interval and a hypothesis test agree? And the answer is always yes. And then they'll say why, and you'll either say 0 is in this range or 0 is not in that range, depending on if 0 is in there or not, and whether you reject or fail to reject HO. Okay. So if you reject HO, 0 is not going to be in that range, like our case here. And if you fail to reject HO, 0 will be in that range, which is not a case we've seen yet. Questions on that one?
Yeah, once again, can you just go over the confidence interval, the 90%?
Where that came from, the 90%?
Yeah.
Yeah, no, that's a common
just-
question.
It's just from the alpha,
confusing.
right? The 0.05?
Right. So
We're
when you see
doubling
an
it.
alpha, yeah. So
Okay.
when you see an alpha of 0.05, your instinct is, okay, let's have a 95% confidence interval, but it's a one-tail test.
And we're turning it
So-
to two-tail to get there.
Right. We're forcing it to
Okay.
be a one-tail into a two-tail. So, if it's a one-tail, we put a full alpha in that upper tail, but when we go to confidence interval, we have to put the same thing in the other tail, reducing it twice.
Got it.
So it's 0.05 minus 0.05, which will get us down to 90%.
Okay. Yep. Perfect.
And if it was a two-tail test, then what we do is we take the 0.05 and we split it, and we'd have 0.025 in either tail to begin with, and then we'd have a 95% because we've already split the alpha, and the a two-tail test and a two-tail confidence interval coincide perfectly then. Does that make sense?
Yeah, that makes sense.
Okay, so it's something you got to be very careful about. All right. All right, I've thrown in a problem from my personal uh, study, I guess you call it. This is where um, my buddies and I uh, we got a grant to test a whole bunch of different fish off the coast of Northern California, and there's many different species we looked at. And one of the questions that we had, this wasn't particularly in the study that we got a grant for, but we wanted to know the answer. And we want to know, do different species of fish have different levels of methylmercury? So the two that we were most interested in, let's see if I can figure this. Let's see here. Sorry, I'm trying to. Okay, so we have two kind of fish that we catch quite regularly. One of this, there's a picture of what's called a quillback. Okay, and a quillback lives right on the bottom. It's a slow growing fish. That's pretty much an average size quillback. I mean, they weigh a couple pounds. Maybe 3 pounds, 4 pounds would be a really big one. But that's what they look like. That's a pretty standard size. But they're a very, very slow growing fish. Okay, and we wanted to compare that let's see, to a canary rockfish that looks very much the same, or well, that doesn't look the same, but lives pretty much the same area. Just this one lives off the bottom, gets similar size. The canary can get a little bit bigger, but grows very, very fast. So, a 2-pound canary is not going to be very old, but a 2-pound quillback is going to be very old. Okay. So our thought was the older, slower growing fish is going to have more methylmercury because over time, it's going to eat more squid and more shrimp and more crabs and more small fish and so forth. And each time that quillback, the slower growing fish, is eating and eating for over years, it's going to get a little bit of mercury, a little bit of mercury, a little bit of mercury, so forth. Okay. So what we wanted to test is, what I came up with basically is use a 0.05 single level to test the claim that quillback rockfish have higher methylmercury levels than canary rockfish. So again, our assumption was made that the quillbacks are older, slower growing fish. They should have higher methylmercuries than the canary. So I do have a little note there. The samples are small. So assumption is made that they come from a population that's normally distributed. Okay, so that was an assumption that I had to make because we didn't have a heck of a huge group of fish that we were paid to catch. We only have whatever 10 or 12 here or whatever that is. Looks like 9 maybe. So let's compare these two. Now the difference between this and the last problem we did is we don't have the summarized data. We have the actual raw methylmercury levels that we sampled, okay, or had sampled, I guess. So we want to compare these, and our claim is that quillback have higher methylmercury. So the first group is larger than the second, so it's going to be a right tail test or greater than. So let me show you how to do that on StatCrunch. I've entered those quillback and canary values in the first couple of columns. We're going to do the same thing as we did before. We're going to do t-stats. We have toSample, but instead of with summary, we have with data because we're actually using the raw scores. We don't have the summarized data like we did the previous problem. Okay. So if we click on with data, we can select those two, the quillback and the canary. Okay. And our assumption that HO's assumption is there's no difference. They have the same methylmercury levels, whether it's a canary or quillback, same. And our alternative was that the quillback has a higher methylmercury level than the canary. Okay, so we're assuming that that slower growing fish has higher methylmercury. We hit compute. Let's see what we have. So, we entered in our step 1. Our alpha is 0.05. Here's our step 3, and here's step 4. Okay. Now our test stat is 4.1. So what that is saying is that the methylmercury levels of the canary and the methylmercury levels of the quillback are 4.1 standard errors apart. So that's a very, very long way apart. Okay, so there's a big difference between the two fish methylmercury levels. And we can see the p-value is very, very small. Okay, almost, just barely above 0. So if we look at that, okay, I have all that in my notes here. We go to our step 5. Since the p-value is low, we reject HO. Okay, so let's think about what happens when we reject HO. We reject HO, that means we no longer think these fish have the same methylmercury, and we concluded that the quillback have much higher methylmercury. Okay, so that's something that we learned. Okay, so we catch both these species of fish, and we learned that the quillback are loaded with mercury. So my conclusion was, okay, that's great. Release the quillback and keep the canary. That way, we're not bringing methylmercury into our family's meals. So that was a great thing to learn for me. So any questions on that? Okay. So now we have our last section for chapter 9, and this is 2 dependent samples, and we have matched pairs. Okay, so let's compare. Let's talk about the difference between section 9.2 we just finished and this 9.3 where it's dependent samples. So the last problem we looked at 2 different groups of fish. We have the canary and the quillback, and those are independent because they're 2 different species of fish, and they have their own lives and they're swimming around and eating shrimp and stuff and all that, and how they live and stuff is different. Okay, so those 2 different groups, not related. Now in 9.3, when we talk about matched pairs, that there's got to be some pairing between the 2 groups. Quite often it's kind of a before and after. Maybe like a weight loss drug. You have whatever 20 people, person A, B, C, D, E, F, blah, 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 and you take their weights and you put them on a weight loss drug for a month, and then you come back and you weigh those people again, and you want to compare person A's weight before to person A's weight after, person B's weight before, person B's weight after. It would make no sense, if we're all doing that survey, it would make no sense to compare my before weight to one of your guys' after weight. I mean, that doesn't make any sense. So we say, okay, my weight before, my weight after, did I, actually lose weight or not? So that's quite often it's, before, after, but it can be some other type of pairing. Okay. So our first assumption is, matched pairs. We have to have a randomly selected group, simple random sample. The group has to be above 30, or the pairs of values have differences that are from a population with normal distribution. So the difference between, before and after weights would have to be normally distributed. Okay. Now we have this test stat. That's what's going to change in each one of these sections. D bars are mean difference. Okay. So if we did this weight loss program and we found the differences in all our weights before and after, D bar is the average of those weights. Mu sub D, that's what we assume is going to happen, or assume that's true. We assume that there's going to be no difference. In other words, we assume that the drug makes no difference in our weight, so we assume 0. S sub D is the standard deviation of the differences, and N is the number of people in the survey. Okay, degrees of freedom is N-1. So this test stat, each one of these is going to change depending on what we're measuring, what we're testing. All right, so let's see how this problem is laid out. Okay, so this it says listed below are the number of words spoken in a day by each member of 8 different couples. The data are randomly selected from the first 2 columns in data set 24 word counts in Appendix B. All right, so the first thing it says, use a 0.1 semi-level test to claim that among couples, males speak fewer words in a day than females. Okay, so we have these couples and they're trying to figure out, does the male speak less than the female or not? Okay. So what we were given in this problem was just these first two rows of data, okay, just the word counts. All this other stuff below it is just me working this out by hand to calculate all these things we need. It's very tedious, okay? So let's just look at this first, whoops. Let's just look at this first group, our first couple, I should say. And, you know, in that first couple, the male spoke 15,000 words and the female spoke 24,000 words. And what we're doing is just finding the difference. So we take the 15,000 minus 24,000, and that's where this 8941 comes from. Okay, so the first one, the male spoke less words. The second one, the female spoke less words, and so forth. So we just find those differences. Okay. And the reason why this is paired is we're talking about couples. So, you know, these first couple, this man, male and female are paired, and they, you know, talk to each other, they know each other, and you know, we have the second group, that is a couple, and so forth. We wouldn't want to compare the number of male the words spoken in this couple by the male to the female in this group. Okay, that brings in multiple issues of, you know, they're not supposed to know each other or shouldn't be probably talking too much. So we don't want to use that as reference. We want to stick, okay, in this couple, which one's speaking more word? This couple, we don't want to mix couples because, yeah, okay. So we have our HO and H1. We assume that the difference between the number of words spoken by the males and females is no difference. And our claim is that the difference is less than 0, meaning that the males speak fewer words than the females. Okay. All this stuff is just done to find the test stat. We're going to have StatCrunch do that for us. And our test stat is negative 0.472. Okay, so negative 472, that's not very far away. So what they're saying is, you know, the number of standard errors between the number of words between the males and females is only a half a standard deviation apart. That's not very far. Okay, so, you know, what we're thinking is the males and females speak about the same number of words. Okay, so when we find the p-value, we do a left-tailed test. So we find the area to the left, and our p-value is the 3256. And in this case, the p-value is not less than alpha, so we fail to reject HO. Okay. So when we fail to reject HO, that just means we don't have enough evidence to rule this out. And what that means is there's no difference between the number of words a male and female speak in couples, okay, which makes sense. Okay. And then our final conclusion, we go to our table. So we can say there's not sufficient evidence to support the claim that among couples, males speak fewer words in a day than females, i.e. they speak the same number of words. All right, so let's do that in StatCrunch. So I have those males and female words in there already. We're going to go to stat. We're going to t-stats because we're using t for our test stat. Now, careful, this is not a two sample. This is a paired. There's a difference between the two sample and the paired. Two sample are two independent groups, like the two different species of fish. And paired is when there's some connection between the two, as in they're couples in this case. So we got to go paired. We select the males and females. Our hypothesized difference is always 0. And our alternative was less than, I believe. I believe that was less than. And if we hit compute, and we entered in the step 1. Step 2 is alpha. Here's our step 3 and 4. Step 5, we need to compare that p-value to alpha. Okay, only if the p-value is low do we reject HO. In this case, it's not. So we fail to reject HO, and then we can go to our final conclusion. All right, and then they want us to build a confidence interval. Now, in this case, we failed to reject HO. So we still assume that one of the options is the difference between the number of words spoken is 0, meaning that 0 should be in our confidence interval. Right? Now, here we have an alpha of 0.05 and a one-tailed test. So if we have our one-tailed test, we put that full alpha, in this case, the left tail. But when we switch to hypothesis test, we got to also put it in the upper tail as well. So that reduces, if we have 0.05 in both tails, that reduces it to a 90% confidence interval. Okay. So if we build that, we take our mean difference plus or minus our 2 standard errors, and we get these mean, the difference in word counts between negative 8,400 words and positive 5,058 words. So what that means, that the negative means that the female is speaking 8,400 more words than the male, and the positive is saying that the male is speaking 5,000 more words than the female. So it can range anywhere in that range. So 0 is one of those options, or is one of those possible outcomes. So that's why we had to fail to reject HO. So again, they'll ask, does the confidence interval and hypothesis test agree? And the answer would be yes. And it's always yes. And then the reasoning is because 0 is one of the possibilities. Okay, it's because one's negative, one's positive.
So for the confidence interval, whatever HO is, if it's included in that confidence interval, that's why we're saying like the reasoning.
Right. So we're always assuming that HO is 0. So in all our cases in this section and every other section, our HO is 0. So if we reject HO, that means 0 is not a possibility, and our confidence interval will not include 0. But if we fail to reject HO, that means 0 is a possibility, and it will be in our confidence interval.
Got it. That makes sense.
Does that make sense?
Yep.
So, when we reject, 0 is not going to be in there. If we fail to reject, 0 will be in there. So in this case, we failed to reject. So 0 was in our confidence interval from negative 8,400 to positive 5,000. All right, and to do this in StatCrunch, same thing. We're going to go under Stat, T-Stats, and Paired. Again, this is paired, not 2 sample. Don't get those mixed up. We would select the male and female. And we'd go down to confidence level, and in this case, 90%. And we hit compute. And we have our lower and upper limit there. Notice that 0 is one of the possibilities in there because one's positive, one's negative. So does our confidence interval coincide with hypothesis? Yes, it will always be true. And why? Because 0 is one of the options there, okay? Which means no difference between those words spoken by the male and the female. Okay. All right, so let me stop there. Okay, any questions on this material or anything else? Okay, so we're going to remain on our Tuesday schedule here for the next little bit. And if you feel comfortable with Chapter 9, you can go ahead and drop off. If you guys have any questions or anything, stick around and I'll answer any of those questions now.
I had one question about the schedule, but I don't know why.
Sure, go for it.
Pearson.
That's fine.
Closed out, so I'm pulling it back up. So next week we're going over